Afternoon. Okay. It's fun. What should we be doing today? I guess mathematics. Um, what particular? Well, actually the field of operator algebras covers all of ground. Well, any field of mathematics, which is developed for any length of time, contains wormholes where people have burrowed into the ground and come up in a different place. So one famous example with operator algebras is everyone familiar with the work of Elliott Vaughan Jones? Well, he did a lot of things, of course, and he started a whole major field of study in phenomenon algebras, where you try to classify phenomenon algebras were classified if they're what's called amenable, okay, with countability conditions. Phenomenon algebras on a separable Hilbert's case, they're classified as a functor. Again, it's a functorial classification. Except in this case, it's only a functor for isomorphism, but that's enough, right? So two phenomenon algebras are isomorphic. Then there's a certain flow, just an ordinary flow. Everyone know what a flow is? Is that a yes or a no? Okay. So for instance, if you've seen a river, that's a flow, right? It can be all kinds of different flows. I mean, sometimes it's what's called laminar, very smooth flow, or it might be quite turbulent. Once on the Ottawa River in the springtime, I was crossing a bridge at what's called Chaudière Falls, and the river is quite narrow there. It's a large river, okay. Well, it's the spring. It was springtime, so you would expect to have more water than usual. But what was happening was it was going under the bridge. It looked like the weight from a motorboat, okay, stretching out like this. But it kept on going, and at its peak, it was a 30-foot high standing wave. That's not quite 10 meters. Right? Everyone still knows feet? I don't know meters. The only thing I know is that if you're talking about a kilometer, the accent has to be on the first syllable. I've gone through that. Do everyone know why? Because besides that it's the law. You can look it up, but because no one ever says millimeter, right, or centimeter. You say altimeter, but that's a measuring instrument. It's not a unit of measurement. It's not the unit of length or okay. What Vaughan Jones discovered, well, actually, you can do it with matrix algebras. You can construct his invariant with just starting with matrix algebras, and one matrix algebra contained in another one. Okay, but no, it would never have happened that way, because people are not going to be too seriously studying subalgebras or matrix algebras. Okay, because that's pretty elementary. So somehow in the sophisticated context, it was so sophisticated that something completely, almost completely unconnected to the original problem, classify subalgebras. of what's called the Murray von Neumann 2-1 factor. And so what is it that came out of that? Besides a lot of mathematics about very important mathematics about subfactors and classification of subfactors. Well, anyone want to put it into words? What's another branch of? Okay, so it was a case where one field of mathematics turned out to have a surprising connection with another branch of mathematics, which but this is the left shoe versus the right shoe, right? The analysis of subfactors. Jones was able to show a very simple knot, the simplest possible knot, simplest non-trivial knot in the whole world, was not the same as its mirror image. Okay, and we got a field model for basically for this. Okay. And it turned out that it was mathematical. It was related more to physics. But you might think maybe that's not surprising with the mirror image, right? Okay. Actually, I wonder if anyone has looked at that. The notion of the fact that a major breakthrough, which is not invariant, very possible, was a concept which is very important in physics in an elementary way. Oh. Okay, but I think that by the way the functor that's used for classifying subfactors is also well, for that matter, classifying factors. This functor I mentioned for classifying factors, the flow. This is because the definition of it is rather similar to the definition of K0 for a star algebra. So for a star algebra, you take projections and look at Murray von Neumann equivalence, right? And you do it for matrices too. Well, if it's if you're looking at the Neumann algebra, well, the K0 is not so. Look at projections, Murray von Neumann equivalence of projections. That's not so edifying. That's not so helpful. We're doing, of course, that. In fact, that was how K theory began. But it's only a question of dividing Neumann algebras very roughly into three types: 1, type 2, and type 3. Roman numeral type 1. But for the type 2 or the type 3, the type 1 is easy to classify because it's a type 1 factor. It's just all operators on some Hilbert space, and the dimension of the Hilbert space, certain cardinal number, is all you need to know. And it can be expressed as an invariant of the algebra. A bit like the supernatural number attached to a UHF algebra. Might take a look at that. Okay, but so you don't look at projections for Neumann algebra. What you look at is linear functionals. Okay, but it's not finite. You don't look at finite linear functions. You want to get a function. Well, in hindsight, looking back, you want to get a flow, right? So how do we get a flow? Well, if it's normalized states, then there's no action of real numbers on, no simple action. What you want to do, what Kahn and colleagues at the collaborators had the idea of doing, was looking at unbounded linear functionals. Okay, they don't have a norm, or at least they're not normalized. But even that actually the ones they wanted to look at weren't even normalized. Or sorry, they weren't even finite on all elements. So it's like the trace on bounded operators. You have a positive operator on the infinite dimensional Hilbert space. It may or may not have a finite trace, right? If it's positive, then if it's compact, even if it's compact, the trace need not be finite. So it's unitarily equivalent to a diagonal operator. It's compact, and it's positive and self-adjoint. And if it's positive, the eigenvalues are we could look at them as decreasing down the diagonal positive numbers. There might be some zeros, or there might not. The trace would depend on whether the sum of the diagonal elements is finite or not. Well, was it trace positive? Then that would be the trace. Well, that's an example of what's called a weight. Okay, it doesn't have to be unitarily invariant to be a weight. And what Farm and co-workers looked at, one of the main co-workers in this context was Dr. Simon. What they looked at was you take weights and you look at Murray von Neumann equivalence of weights. You treat the weights like production. Okay, so it's almost the same as unitary equivalence. Okay, which is easier to define. Even for productions, unitary equivalence is easy to define. For arbitrary operators, it's easy to define. Unitary equivalence. This means it's a unitary, and they conjugate one together with unitary. And since if you have weights, then they have an algebra, then they have every weight has a support, which is a projection. Okay, it's like the support of a measure, projection on which it's on the orthogonal complement at zero. Okay, and if you have two weights, then you want these projections to be for the weights to be equivalent, and they're not unitarily equivalent. You want the projections to be equivalent in such a way that after all, the weight is concentrated inside the production, so you just take one weight on the other. So that's Murray von Neumann equivalence of weights. The key step is you take one of these positive functionals, and if you multiply it by 2, you get another one. Or you multiply it by any, we'll say non-zero positive real number, then you get another one, right? But this is if you look at the positive non-zero real numbers, as a group, that's just the whole real line, right? So you have an action of that. That's a flow. So that's the flow of weights. It's called the flow of weights. Okay, and it passes to the equivalence classes. So that's it. It turns out that it's I think an arbitrary flow, like arbitrary flow on a measure space. And you can express it as you can express it if we're talking about well, if it's trivial, then it's just a flow on a single point, trivial flow on a single point. If it's non-trivial, then it comes from a factor, it means the center of the scalars. Then it's you just look at L infinity of the interval 0, 1, okay, and you look at a one parameter group of automorphisms of that, and that's an algebraic formulation of the notion of flow. You can have a flow acting on the measure space itself or on the L infinity space. Okay, so that was that's an example of a classification function. Flow of weights. Well, and I'd like to spend some more time between now and the end of the year. We'll have to take a break for Christmas. Well, I don't know if we get a chance to continue after. Normally, often I give a course in the second term. This year I'm not. But, um, well, so we're in this course we're talking about K theory and basically Marie von Neumann problems. And it's Easter algebra over the organic algebra over the complex scalars. Then there's K0 and there's K1, and they're somehow sort of related, right? And over the reals, it's more complicated. You have K0, K1, K2, K3, and so on. But over the defined in terms of the repeated suspension. But, complex numbers, so you could define the K groups by the repeated suspension, but it turns out you get very soon you get back to where you started. So and there's a way of codifying that, which is very useful for calculations. I'm not sure. So it's numbers, you have, remember there's a bit of work required to go to non-unit algebras. So to go, because the ideal would be non-unit to get that anyway. Does everyone remember why I have that here? There was a trick. You have two productions at the corresponding K0 class, so we can assume, let's assume the big algebra has a unit. And the K0 group is the difference of the K0 classes two productions. But it turns out you can take one of the productions to be the unit, or maybe the unit and then the matrix. That's quite important because if we want to get something coming K0 with the ideal, that means we're looking to be K0 into K0 with I tilde. Well, want the K0 by tilde, we want to well, we want to be in I if it's in K0 of I tilde, for it to be K0 of I, it's so we want the image to be 0. Well, here if you look at this, the image is 0. We prove exactly exactness, and you assume that the image is 0. And then you reduce to the case that these two projections are unitarily are equal. You reduce to the case that these two projections in the quotient are equal. Okay, but how does that help? So E minus 1 sub n belongs to I. But we got stuck with that when we weren't working with the unit here. So why does it help, Jack? Why does it help to have the unit here? So we want to prove that. So of course the image is we map from E is equal to 1 to log I. That's the case with this instead of just an F. What's special about the case, about having reduced to the case that E is equal to 1 modulo I? Well, we're just an arbitrary F. We wouldn't know what to do. But if we want to prove that we want to get something in K0 of I tilde, right? In other words, we want to get projections in I tilde. Well, 1 sub n belongs to I tilde, right? Or matrix algebra. And E minus 1 sub n belongs to Y. This is you don't believe this is going to happen. Okay? Therefore, because we're working with groups, additive groups, therefore E belongs to I tilde. And we've got two projections, E and 1 belong to I tilde, and they're equal modulo of the ideal. So that means it's a K0 class coming from it's the image of a K0 class in I. Well, okay, so that's exactly here. By the way, we should check that if you do start here and you go twice, then you get 0. Okay. Has everyone checked that? Abigail, have you checked that? We start with something here. In other words, you start with something here, say E and F. And minus F. Y. That's more or less what we produce. We know it's very equal, and of course, we don't know why it's 0. So, we look at them in K0A. Well, of course, they may not be. It's in the K0 class E minus F in A. May not be trivial, but if we pass to the quotient, then E and F are equal. If you have two projections in A over I which are equal, then the K0 class is 0. Anyway, that's called half exactness. But and there's also the K1, so I get like and if we define K1 as K0 of suspension, which is not too hard to prove. If you did define it as in terms of verticals begin then we get half exactness here because suspensions. We have a short exact sequence of algebras, the manic algebras, the suspensions also give you a short exact sequence. You have to check some. And comparing SA mod SI with S over I. I have to show that those are the same in a natural way. But what's the point of putting the two side by side? Well,
we have index maps, right?
yes. Sorry?
We have index maps that go from.
Oh, right, yeah. That's exactly that's exactly the. Oh, this is a fundamental, one of the ways of stating the fundamental facts about K-theory of Banach algebra, complex Banach algebra. Well, even for real Banach algebras, the even index map ends up in K0 is defined. And if A is the algebra of bounded operators and I is the algebra of compact operators, then every unitary in the quotient A over I is the image of either an isometry in A or something that's adjoint to the isometry. That's called a co-isometry. That's not hard to prove. That's a good exercise. And furthermore, the isometry, it's a co-isometry. That means it's not injective, it's a kernel. That kernel will be finite dimensional because the modulo I is inverted. The kernel goes into zero. The kernel is a projection onto the ideal compact operator. So that means that the operator has index. You have an operator on a vector space that has index. It's the kernel and the co-kernel are finitely generated. Okay. Finitely generated in the vector space. You have two finite numbers, two natural numbers. The index is the difference of those two numbers. Sort of convention which one you subtract from the other one. Which one? Well, okay. And then this is something which is it's called Fredholm index. I probably told you my story about having breakfast with Fredholm once. Oh, no, it wasn't Fredholm. Who was it? It was Fredholm's nephew. Fredholm's nephew. And trouble is, by the time I found out he was Fredholm's nephew, he was gone. Would have liked to thank him. Well, I don't know what I would have been thanking him for. But anyway, he was interested that he was already interested that I was visiting the Mathematics Institute at university. And so he might have gotten a kick because I was basically working on the subjects. One of the main concepts related to my work, Fredholm index. Because after all, I'm doing K-theory, you might say, when it's Schuster algebra, and index is special case of K-theory, index map, natural map, K1, and quotient to K0. And we just talk about Banach algebras and extensions of Banach algebras. I've pointed this out, and I have a paper which talks about the uniqueness of the index map, Banach algebra K-theory, which is a natural map. K1 is the quotient, K0 is the ideal. Forget about exactness and the rest of it. Just to have a map which is natural when you compare two extensions, two short exact sequences. Well, if B is sitting out here and J, the ideal J is sitting out here, and then you have a diagram. And then two maps, two candidates for the index map are related by that natural. And that's true for whenever you have extensions. Banach algebras, if you have extensions Banach algebra, then that this map is unique. What does unique mean? It means any two such maps, any two such universe, two such generally always defined maps for every dimension. Any two of them have a common multiple, a common integral multiple, or they're both multiples. You don't even have to state that it's unique. You don't have to know there is one. Okay, it's the ones that do exist form a group isomorphic to and if they, of course, if they don't exist, and if they didn't exist, then it wouldn't be any group. It'd be the zero group. But if you have the zero map, it always has something. So, but the statement is it's the group Z, the group of these maps, universal maps. Does that make sense? Okay. But it's, in other words, even without exactness, it's the index map. This abstract level is very natural. In fact, unique up to integral one. Of course, you can't pin it down. Even the definition, even when you're defining a particular one, it's hard to. You can't really separate it from -1 times it, but you have to decide which two spaces to subtract. You have to decide on the order of subtraction. Well, okay, and the idea is once you have this one, if the block periodicity which flips 2 rows, then you have this one. And the funny thing was you could define this one using the complex number I. You couldn't prove exactness very easily. The way you prove enough of block periodicity to flipping is you take a very special case of this, very, very special case of this, okay, where the extension is the cone over some B. Quotient then is B. Quotient is B. And then a kernel is the suspension. So the suspension, well, B is B. And the suspension is functions on the line vanishing at infinity, either side. And the cone has functions which vanish at -infinity. But at +infinity, they just converge. So what they converge to in +infinity, that's how you get the quotient. That's the case in which so then proving we have exactness here and here. Well, by the way, it's the cone, then these groups are 0, okay? And so you have to prove isomorphism, but that's the isomorphism from K0 of B to K1 of S of B. That's how that explains well, it shows how it explains why this is called the 6-term exact sequence of block periodicity. Okay. It's something which is universally true for real scalars. So one sloping line, which you only have functions. Okay, well let's review the proof of this isomorphism. So exactness here, exactness says these are 0. Exactness here says the map is objective. And exactness here says the map is surjective. And the strategy is we've discussed is you first prove surjectivity, and then as a special case you get injectivity. Okay. Has everyone thought about how you get the injectivity? Oh, you can look it up, right? You have 2 K0 classes. They have 2 projections. You see, each K0 class has a single projection. We're talking about the difference of something with a multiple of a unit. And I guess if you're comparing 2 K0 classes, you can add enough of copies of the unit to so you're comparing just projections. And you have, so you look at two projections and you look at the basic path, the fundamental path. P prime projection. Look at PZ and P prime Z, and you round them off to be vertical. If you find K1 just inside of projection, so if suppose these are homotopic through a path of invertible paths, okay? So we want to prove this is injected. So we have two k-zero elements. These are the, and then we look at the corresponding loops. K1 classes of the loop. And that's what these are. And we assume these are connected. Okay, homotopic, that's what equal in K1 means. We assume there's a path, an ordinary path, not a closed path, it's a path going here to here. But then that's the same as working in the beam tensor C01. We just have a and the point is this path takes place in the matrix algebra, okay? And it's not linear. Points in the path, intermediate loops in the path. They're not linear loops, okay? They're just polynomial loops. We don't even know they're polynomial loops. We have to go through the whole business of surjectivity. Look at the proof of surjectivity. Then you get that in some large matrix algebra, there is a linear path. There's a path of linear loops going from here to here, okay? But then it's pretty easy to see if you have two paths like this homotopic, the projections are homotopic. Okay, that's the end of the proof of injectivity. Using surjectivity. Surjectivity got that in some in some large matrix algebra, this path, this ordinary path of loops of invertibles was homotopic to a path of linear ones. Okay? Coming from a path of connections. All right, so that's a review of all. So what was this? Classification. What periodicity you have this schematic outline, right? And then you can say that as a corollary, you get injectivity too. This first step one was constructing the algebra, mathematical level of algebra. And then you have to check that it gives you a group math. Okay. And then actually blowing up the matrices. And what does the blowing up to matrices entail? We have these two polynomial loops. By the way, I suppose that we have there's always the schematic outline of the AF algebra proof. This certainly deserves to get filled in. I would call that an exercise at the very least. If anyone wants to fill in the schematic outline for AF algebra isomorphism theorem using the ordered K0 group together with the class of the unit. special class. And that would be very welcome. Could have very good exercise. Okay, but so what do we do? We want more space. So if it's just complex numbers, well, complex numbers don't have much space, but you don't need much space. If any path of invertible complex numbers, okay, or unitary complex numbers, any path from the circle into any closed path inside the circle, going around a certain number of times one way, then the other way, and so on. But then it's elementary that you can always homotopy something like that to a linear path, which means that to the end for some end. And no matter how you homotope it, you only ever get one n. Okay? The n is an invariant, a homotopy invariant. And if two paths have the same n, then they're homotopy. Well, that's kind of obvious. Each one is homotopic to z to the n, then they're homotopic. So this doesn't quite solve the general question for K1. For K1, you have to look at matrices. Now, well, this is a kind of it's just sort of a diversion talking about special cases of the complex number, what previously involved, because I said that those almost when I said you have to repeat the proof for the general C-star algebra, the general dynamic algebra in the case of complex numbers, I didn't mean that literally, because there is a proof special for matrices, but you don't want to. It's worse than the proof for you have a path of units, a closed path of unitaries with the endpoints just the identity element of the algebra. And it turns out you can homotope it inside the algebra itself into one of these paths with z to the n, for if you allow n, not just z to the n, go inside the algebra itself first. In our case, that's not true. By the way, in the case of a finite algebra, it's also true. And so I would give a reference to the, I referred to the paper of Fuji, Rocky, and his two friends, Mustafa and Larry Smith. It's an elementary discussion, which was a pioneering work in quantitative case theory, quantitative system that wasn't recognized at the time. They just showed that had a loop of invertibles inside the finite factor to the matrix stuff. And it's homotopic to one that comes from projections power of z. That's like this. But inside the algebra. And it's quite the proof I was talking about for matrices. It's quite different from the proof of Araki and Smith and Smith. It might be easier. Proof of that's a good exercise check. The proof of Araki, Smith, and Smith applied to matrix algebra is easier than the proof I'm suggesting involving taking the unitaries in your closed path and perturbing the whole closed path. So for every one of these unitaries, the eigenvalues are distinct. So if it's 100, 500 matrices, then every one of these unitary matrices has 100 distinct eigenvalues. If you can do that perturbation, then after that it's easy because you just straighten it out. So every one of the eigenvalues is z to the n of some n. Then you make the eigenprojections, form one-dimensional projections, eigenprojections into constant projection eigenvalues. So you have your final task of single diagonal matrix with different powers of z up diagonal. And if you want, you easily put them all up into one place. Yeah. Okay, so that's but making the eigenvalues distinct. That's it's outlined in my well, the truth is published, referring to earlier things in my real rank zero paper on classification of the limits of matrix algebra. On the classification of these two algebras, real algebra. And it's published in perhaps the very oldest, but started by the German mathematician Relin. It's other papers. Okay, so it would be interesting to see what the Rafi Smith statistic with the Rafi Smith is in the communications in mathematical physics. 1970. Maybe this is 1993. So this is really 1971. This is before anyone was talking about K theory and yeah, here's the so well, I was going to check here. Well, I should. That's embarrassing to have to say that because I should just be able to look for an instant, right? Especially since a lot of people are very helpfully sitting in the same place. Okay, but I do seem to have some trouble recognizing Husam and Abigail Axel, Jack Sloan, Yuja Teng, Carissa Kilby, Arca Prado 2-3, Charlie, and Siddharth Dagmar. Okay. How are you doing for homework? Yes, send me an email if you want to talk about Daniel Ding. Plus. See what I mean? I just hopeless. Send back your memory. So, last two people, again, if you have any questions about the homework, please stay in touch. Charles Griffin. Dan May Glover. Henry Hooper. So, thank you. Jalal Kelsey. Alexander Cole. Charles Chang Bin. Glenn E. Brogan. No, that's not. So he's on? Yes. Ife Luz, what about him? Or she? Uh, I haven't met her. Yeah, I haven't met that person. Luke, the cut. Yeah, thank you. I think you're just a little closer than last time. Good, good. Abu Bakar Mohit. Ruben Navasarda. Thanks for your estimate. Well, I wrote some comments about phenomenon algebras. Did you have any questions about that? Jonathan, what are you doing for second? Do you have a second topic for your plans for second?
I'm trying to decide.
Okay, good. See you at Mohammed present. Or Larry, it's fine. Give on one. One goal, one. As I see, going here, okay, so. Yes. Well, I've talked about what the classification is of well-behaved simple C-strong. You look at arbitrary abelian groups, right? Arbitrary countable abelian groups, and those are the K0 groups and the K1 groups. And that's quite a tall order, right, to look at all those countable abelian groups. They're not necessarily torsion-free, not necessarily subgroups of a rational vector. There's a structure theorem for finitely generated abelian groups, and any countable abelian group is increasing the union of increasing sequence of finitely generated subgroups. So how you can say something. But okay, so it's these two groups, but now the K0 group does have an order structure, but you don't need to know it because traces pair with K0. If any projection, you can take the traces projection. And if it's a non-unital algebra, then if you join, you can't join a unit because the trace of the unit might be infinite. You want to have a positive trace. But there's a trick. You join a unit, and then you say you extend the trace to the algebra unit to join in such a way that you just say take the trace of the unit to zero, but not a positive linear function anymore. And no, this trace is not positive on the. It's not finite valued on the algebra either. Maybe it's a stable algebra. If it's compact operators, then the trace is not finite on the algebra. You don't get a finite linear function. But if you look at what's called the Peterson ideal, it's a dense two-sided ideal. Well, in the case of the compact operators, it's just a finite rank operator. And of course, every finite rank operator, the trace is a linear functional, an ordinary linear functional, and finite rank operator. Right? Yeah. Okay. So I get a linear functional that way on the algebra unit, and that's a trace, a non-positive trace, but it still pairs with K0. It's beautiful.